Hello everyone, welcome back to Labtube. In this video I'm going to do question 17 from section 16.7. The question asks to evaluate the surface integral. It is written there, x squared z plus y squared z ds, where s is the hemisphere given by this equation x squared plus y squared plus z squared equals to 4. That's the equation for a sphere, centered at origin and radius equal to 2. But we're just taking hemisphere, that means z is bigger than or equal to 0, so we're just taking the upper hemisphere for this integral. Okay, things that you have to know to be able to do these questions are this. One, if you're going to evaluate a surface integral and the surface is described like this, it is a sphere, it is something given by some equation or some parameters. The first thing is that parameterize the surface. Meaning that find a vector function r uv such that when you value of uv's you cover that surface. So you not only need to find that, you also need to find the boundaries or the region on which the parameters vary. So that's the first step. When you find that, then the second step is that you can evaluate the surface integral. Meaning that you have S, F, ds. You need to do 3 steps to evaluate your integral. First step is plug in boundaries of the region for the parameters. So we'll do example and you'll notice. In this description you will get a region and then you need to describe it, and then you just plug in those in the boundaries. Then the second step is plugging your parameters in your function, meaning that your vector function, which describes the surface, has 3 components. The first component you put for x, second component for y, third component for z. And then for ds, you form this thing, you find partial derivative of r with respect to u, find partial derivative of r with respect to v, cross product, then find the length, and then find uv. Okay, great. Now, if you can do that, then your surface integral turns to an integral, which is double integral, and you can evaluate that double integral. Do inner one, then do outer one, and that will give you an answer. Okay, that's what you need to know for this question. But let's go back to our question. Evaluate surface integral on the hemisphere given by this. Okay, there are different ways to parameterize a surface. Important thing to know here is that this integral is independent of parameterization. It means that it doesn't matter which parameter you use. If I use one parameter, Michael used another, Alex used another, Malaya used another one, we have to get exactly same value. Okay, I am going to do this question with 2 parameterization. Let me start with the one you all know and it is easy to follow. So, parameterization. For hemisphere, upper hemisphere. So, best thing to describe spheres in R3 when they have origin, center at origin, is using the spherical coordinates. So, if I want to describe Spherical coordinate has three pieces. One rho, second phi, then theta. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. So you just do that. And then, but what is the description of that? In this case, I'm just taking sphere. So my rho, the distance from the origin, is going to be equal to the radius of this sphere. So rho is going to be square root of 4, which is 2. Then in spherical coordinate, you have to remember that x is given by rho cosine, sine phi cosine theta. Y is given by 2 sine phi sine theta, and z is going to be equal to rho times cosine phi. Okay, so that will give a parameterization for the sphere. But which part of the sphere we want to have? So you have to see first theta. You have the whole theta to cover the upper hemisphere. But to have upper hemisphere, your phi goes from 0 to pi over 2. So d for us, so our phi and theta are inside this, are all phi and theta such that phi goes from 0 to pi over 2, and then theta but goes from 0 to 2 pi. Okay, that's good. Then that's the parameterization. Now we can start working with this. I have the parameterization. I have to apply these 3 steps. Let's do this part first. So I want to find what is our theta. First, our phi. Let me do first our phi. Our phi. Find partial derivative of this vector with respect to phi. It is equal to 2 cosine phi cosine and theta, 2 cosine phi sine theta, and then minus 2 sine phi. Then I have to find partial derivative of r with respect to theta. It is equal to negative 2 sine phi sine theta, then 2 sine phi cosine theta, and the last component is independent of theta, so its partial derivative with respect to theta is going to be 0. Okay, great. Now I can find the cross product. Let me find it here. So r phi cross r theta. So I have I, j, k. I have 2 cosine phi cosine theta, 2 cosine phi sine theta, minus 2 sine phi, and then minus 2 sine phi sine theta, and then 2 sine phi cosine theta, and 0. Okay, since I have to apply this all. Okay, then first component, this times this minus this times that. So I will get minus times negative 2, it is plus 2 sine phi times this. So I get sine square phi cosine phi. That's the first component. The second component is this times that. It is equal to, there is 2 times 2. I have to get 4 here. And then for this one, I get 4 again, sine square phi sine theta. And for the third one, I have 4 cosine phi sine phi times cosine squared theta plus 4 sine phi cosine phi times sine squared. That's the third component. Okay? But note that in the third component, I can factor out 4 cosine phi sine phi, and the remaining part would be cosine squared plus sine squared. So the third component can be simplified to just this, 4 times that. Okay, now let's find the length of this cross product. Okay, this squared, so it is 16 times sine to the power 4 phi cosine to the power 2. This is theta. This is theta. I made that mistake there. This should be theta. It is there. So it is sine to the power 4 times theta plus this square 16 sine to the power 4 phi sine squared theta plus 16 times cosine square phi sine square phi. Okay. There is simplification here you can do. Factor out 16 sine to the power 4 of phi from these two. The remaining part would be cosine squared plus sine squared. So the first two terms will give us 16 sine to the power 4 phi. Sine squared plus cosine squared is equal. Okay, and the third term, I can also factor out sine squared. So I can factor out sine squared, and I get so 2 sines coming from these two terms plus cosine squared. Then again, I have sine squared plus cosine squared. It is equal to 1, and then factor out all these things. It is 16 root 16 sine phi squared, and it is equal to 4 sine phi. Okay, so I have done all those computations, but the important part is just the length of this guy, yes? And length I found it is going to be, so I can erase all this thing and I can write r just length of r theta, partial derivative of r with respect to theta cross partial derivative of r with respect to phi is equal to 4 sine phi. You can remember, you can check this from the fact that the volume for the spherical coordinate is equal to rho squared sine phi. Rho in this case was 2, so I got 4 times sine phi. Okay, so I can erase now all this thing because these were all to find that term. Okay, so I have that. Now I can go ahead and try to do this thing. So if I am integrating x squared z plus y squared z ds, this is going to be boundary of my variables, my new parameters. These are here. So I go from 0 for phi, I go from 0 to pi over 2. For theta, I go from 0 to 2 pi. Okay, that's good part. Then the second step is plugging your parameters in your function. For x, we have to plug in this thing. So for x, I have 2 times, it is x squared. So I have 4 sine square phi cosine square theta times z. Z is given by this, so I can multiply that here, and I get cosine phi plus y squared. So it is 4 times 4 this squared sine square phi sine square theta. Okay, then multiply to z. Again, I multiply this to z. 8 sine square phi sine square theta cosine phi. Okay, that's the second step. Then time this whole thing here, so it continues to here. Length of this, which is 4 sine phi, so all these things multiply to that, d phi d theta. Okay. Okay, now I can do some computations here because look at here. So I can factor out cosine phi sine square of phi. So I will get 4 here, 8 there. So I'll get 32 sine square phi cosine phi. Sine square phi is here, cosine phi is here, sine square phi is here, cosine phi here. I factor out 8, I have another 4 there, so it is 32 times that. But the remaining is cosine square theta plus sine square theta, which gives us 1. Yes? And then multiply this to sine phi. Yes, that's good. Now we have one big piece of double integral, and we have to do the inner one, then the outer one. Let me rewrite this integrand as I have sine here, so I can write this sine cubed d phi dt. Then look here what I have. I have sine to the power 3, and its derivative is here. So it's basically you're integrating u to the power 3. If you integrate that, the antiderivative of this guy is going to be sine to the power 4 phi, 32 divided by 4, and then you go from 0 to pi. In other words, I use this substitution. I say t is equal to sine of phi, and then dt, which is cosine phi d phi, is here. So I have u t to the power 3, its antiderivative is t to the power 4 over 4, and that's it. Okay, then now let's plug in values. Sine of pi over 2 is 1. Sine of pi over 2 is 1, so it's 32 over 4. Okay, 32 over 4 is 8. 8 times sine of the sine of pi over 2 is 1 to the power 4 is 1 to the power 4 minus 0 to the power 4 times d theta. Okay, this is 1 times 8 d theta. It is going to give me 8 theta, 0 to 2 pi, and that is equal to 16. Okay, so what we did here in summary would be, first I wrote this surface in this form, parameterized it in spherical coordinate, and then I found the integral element, which is given by length of ru cross rv du dv. In this case, I got this, which is 4 sine phi. And then I followed these 3 steps here. Change boundaries, plug in new parameters, plug in the line integral in terms of your parameter, and then you got a double integral, do evaluate inner one, outer one, that's the value you're looking for. Thank you for watching this video, and thanks. What's that?